Hi, my name is Brittany Zhao, and I will be talking about a machine learning project that I worked all throughout this quarter. This is fall quarter 2022 at UCLA for Math 156. And our project works on image recognition of the American Sign Language alphabet, or ASL. So just to give a little bit of background on what this project is all about. So for our machine learning project, me and my group decided to work with American Sign Language and specifically the alphabet. So for those that don't know, those with hearing impaired may find difficulty speaking as people with normal hearing would. So because of that, American Sign Language was made to bridge the gap between hearing impaired and the speaking world. So American Sign Language uses symbols and gestures to convey words, phrases, and letters of the alphabet, like so. So a big problem, though, in this industry is that there's not many resources that are able to translate and interpret American Sign Language between others. So if someone fluent only in English and someone fluent only in American Sign Language were to try to communicate with one another, there would oftentimes need to be an interpreter to be there to bridge the gap between the two. So our goal was to make a resource that could assist in ASL translation using machine learning. And now, obviously, given the time constraints of this project, we would not be able to create a all-inclusive dictionary. So because of this, we decided to focus on the 26 letters of the ASL alphabet. So there are 26 symbols, and that correspond with the 26 letters of the American alphabet, or the English alphabet. So to create this model that would be able to identify each letter, we decided to create a convolutional neural network, or a CNN, to translate what letter is being signed in a particular image. So to work on this project, we would need a big data set to train a model with and be able to identify which letters correspond with which images. So this was the data set that we were working with. We got it from Kaggle, but as you can see, we have actually 29 different classes rather than 26. We have the letters A to Z. We have a delete character, a nothing image, and a space image. So theoretically, with this alphabet, anyone would be able to communicate anything from ASL to speaking and vice versa. So to first start out with this project, because our ultimate goal is to be able to identify an image of a hand with the correct letter of the ASL alphabet, we first wanted to pre-process this data because, as we can even see here, the lighting of the letters A through F in the sample image is very different from the lighting in these last few letters, W, X, Y, Z. So to standardize it and try to take out as many confounding variables as possible, we decided to pre-process this data before running our model on it. So to pre-process it, we decided to do a whole bunch of things to it. So this is an image of the actual pre-processed data. But from here, we added a couple things to it. So we first added a layer of padding, which is just a certain number of blank pixels to the border. And this was just to ensure that every part of the hand was accounted for. If you can see here, sometimes it can get a little bit cut off. We can see a finger is right up in the edge right here. Same with the letter D, it's really close. Z up here as well. And so because of this, we just wanted to add padding to the border to ensure that the pixels in the middle were still accounted for and the entirety of the hand was still still readily available for the model to recognize, and it wouldn't skimp out on the pixels that are closer to the border. So we first added some padding to minimize that. We also randomly cropped the image after adding the padding, and this was to just off-center the hands a bit. So it might be difficult to see, but because they're in different spaces as well. But if you can see, if we look at N right here, this is where the hand is, and you can see that we slightly have moved it down and to the left a bit. It's a very subtle change, but we were mainly just trying to make sure that the hand was not always in the center of the image, because oftentimes, if practically speaking, someone were to take a picture of their sign language or their hand gesturing a sign language letter, it wouldn't necessarily be in the center of the image. So because of that, to counteract this, we decided to crop the image randomly. We also decided to rotate it for a very similar reason, just to realistically depict what a hand would look like naturally when signing. And it's not always necessarily going to be upright and completely straight. So we decided to randomly rotate the images as well. The biggest change, or one of the two bigger changes that you can see from the pre-processing data is the removal of the background in the processed data. So if we again go back to the original data set, we can see that in the background there can be a whole lot happening in the background, and we didn't want our model to at all worry about that, or even have that be a potential that could impact the model. So here we can see in the background there's this blue part and a white part, there's this edge up at the top, and there's a lot going on. But using edge detection, we were able to be able to identify the hand first and remove the background like so. So this ensures that our model only looks at the actual signing hand that is in the image. And then the final thing, and again, a big visual change, is grayscaling the image. And we did this to just reduce the complexity of the image and hope for slightly lower computational power needed to actually process the image, and as well as reducing the bias, at least slightly, just to make sure that there would not be any colors that were impacting the overall efficacy of our model. So this was the pre-processing portion of our project. And moving on to the actual model. So as I mentioned at the beginning, we decided to use a convolutional neural network model to properly identify which letter is being signed in the image. So because it's a convolutional neural network, it, as we have learned in Math 156, for those of you that don't know, convolutional neural networks tend to have a convolutional layer alternating with a max pooling layer, and then it flattens the data, and then it has alternating dense and dropout layers. So that's the overall architecture of a CNN, which is also a convolutional neural network. But just to go into detail of our model specifically, since it is a CNN, the first layer we have is a convolutional layer, and we decided to use a 3x3 kernel, and basically in overall, what a convolutional layer does is reduce the complexity of an image without dropping or losing any important data. So in this case, we take a kernel and we apply it to every 9 adjacent pixels, or 3x3, and condense that into 1 pixel. And to do so, this reduces the dimensionality by 1 pixel on each side of an image. But ultimately, this kernel will take the most important information and condense that into that 1 pixel. So that's what the convolutional layer does. From there, we have a max pooling layer, and we can see that in pink right here. So max pooling layers are also very standard in CNNs. And what they do is they drastically decrease the size of the image. So we use a 2x2 max pooling layer, and this reduces the size of the image in half. So what this layer does is take the maximum value in each group of 2x2 pixels. So once we run a image through that, our image ultimately reduces by half. So that's how we can see this first yellow convolutional layer suddenly decrease in size to this pink. So that's the immediate reduction in size. And this still retains the necessary information while significantly reducing the size of the actual image that is being processed. So our model So those are the two different types of layers in this first part, and we alternate between these two. And this is overall what a CNN does in the beginning portion of the model. So for our model specifically, this diagram represents this, and we also have it shown here in plain English. But we have a convolutional layer, max pooling, convolutional, max pooling, etc. And this alternates 4 times for our specific model. So we can see the convolutional layer here. We can see the half size and reduction. Again, 1 pixel reduction, half size and reduction, 1 pixel, and so on. So that's the convolutional layers and the max pooling layers. And we also have a flattened layer, which is right here in this aqua color. And it can also be seen right here in the plain English version of the model diagram. So the flattened layer is applied just so one-dimensional output is created, and this is necessary for classification. So in this case, we're classifying our data into one of 29 different categories. So we need that just so we're able to classify the images properly. After that, we have dense and dropout, which is also being alternated here, dense being this light blue and dropout being this dark blue. So in a dense layer, each node is then connected to all the nodes in the previous layer. And in the dropout, we have a specified fraction of values that is set to 0, while the remaining are scaled so that the sum of the input values still remains the same. And the main purpose of this is to prevent overfitting of our data. So in terms of this model specifically, we alternate between dense and dropout, etc., etc. And this happens 4 times in total. So we have dense dropout, dense dropout, dense dropout, dense dropout, and we end it finally with a final dense layer. And this final dense layer has 29 nodes specifically for our model. And this corresponds with the 29 different classes from the data set. Reminder that the classes are A to Z, which are the 26 letters of the ASL alphabet, alongside space, delete, and nothing. So altogether, this is our model in a whole. We can also see it written out here. So we have convolution layer, this is the input layer, which is all the data, convolution, max pooling, etc. And we have our flatten, our dense dropout alternation, and our final dense layer right here. So this is the architecture of the CNN as a whole for this project. This is the model written out in code. So this is the actual model that we did run on the data set. So we used Keras and Python as a language for actually encoding this model. But here we can see the alternating convolutional and max pooling layers right here. We have the flatten, and then we have the alternating dense and dropout, and then the final dense layer. And this is the output layer, as we had mentioned earlier, with the 29 nodes. So this is the model itself. You can also notice in this code that we use the activation function ReLU. This is used, and it's very common in CNNs for image classification, but the main purpose of using this activation function is because we want a non-negative activation function so that the other representations of the image will not negatively impact the output layer. So because it's always non-negative, that prevents this from ever happening. Additionally, the gradient of ReLU is always the constant function 1, so there's also no vanishing gradient. We don't end up ever resulting in that. So from there, this is our model as a whole. So here, using this model, we then trained the model using 80% of the data and then tested it on the remaining 20%. So for here, we first, again, as I mentioned earlier, in terms of the process, we pre-processed the data, then we ran the model through the pre-processed data, and then ended up with these results. So we ran the model through using 10 epochs, and we can see here the accuracy increase, and hit around up here. We also see the actual test. So this is the train accuracy, hitting about at around 95%. And then we can see the actual value of the test accuracy. And again, with each epoch, it does slowly increase, but it does stagnate around 5 epochs, but we ended up getting a test accuracy of 0.9, right around here at 10 epochs. Again, and then on the right, we can see the loss function being calculated. So the blue being the train loss function, we can see it slowly decrease in value and trend to 0. And with the test data, again, we can see the decrease. And while there is a bit of a spike here, we do see a downward trend. So just explicitly seen in the numbers themselves, this is the test test data set accuracy and loss. So we have the accuracy being 0.9 or 90%, and the loss function being around 0.4. So just to discuss the next steps regarding this project, as mentioned earlier, ASL has a vast dictionary of words, phrases, and other symbols representing numbers, symbols, and etc. So this project by no means is a comprehensive way of representing and translating between speaking people that speak primarily and people with hearing impaired that only use ASL to speak. So some next steps in terms of how to improve this would definitely be adding numbers and other static words to this model specifically. So if we were looking to build on this CNN model that we have created with image recognition, we could definitely add other words and numbers that use images and would be able to be accurately represented in a static image. One method that we could use to actually achieve this is transfer learning, which uses a pre-trained model, which could be the one from this project itself. So this pre-trained model has already been trained on a large data set, and using this model, we can then transfer the weights from that original model onto newer ones that require new data. So this could definitely be one extension that directly extends from our work on this project specifically. But one ideal extension of this project that would require a lot more research and require a lot more time and effort, definitely, and computational power is video analysis. So there are two letters in the ASL alphabet, those being J and Z, that use movements to actually properly convey the letter. So in this data set, the way they represented J and Z was to only represent the final frame. So in this image, we can see this is actually the final frame of Z. But in reality, the actual letter Z requires some movement. So because of this, there is some limitations to only using static. There are actually many limitations to only using static images for translation between English words and the ASL alphabet. In addition to this, the alphabet is a definite way to communicate between an English speaker and a ASL speaker. However, in reality, ASL users will use certain phrases and have signs for certain common phrases. So as an example here, in this little animation, we can see this girl saying, "Hello, my name is Sammy," and she is not spelling out every letter to convey the sentence. She's purely using a couple of signs to be able to convey that. So we would definitely love, as future work, to look into video analysis to extend to these movement-based words that would be a lot more useful in communicating with an actual ASL speaker rather than solely just the alphabet. So these are definitely areas of interest and would definitely be a lot more applicable and more useful in everyday society. But I think that for this project's sake, focusing on the alphabet and using static images was definitely a great proof of concept and a step in the right direction in terms of bridging the gap between the speaking population and the hearing impaired. And yeah, so that was my group's project on image recognition of ASL sign language, specifically the alphabet. I had a great time researching this project and actually computing it. So yes, it was great to see the application of math and machine learning in a very important and relevant topic. So thank you all for listening. I hope you